Thank you, Patrice. So this techno-economic assessment has been done with Total Energy and also with Syntec, Simon Busanali and Rahul Anataraman. So now what Patrice says that we have a design for an industrial scale unit. So forget about the 3 megawatts. Now we are on the real one, 500 thermal megawatts. And the TEA is there really to say how much cost this industrial scale unit, to be able to provide some KPIs like the levelized cost of electricity, how much it costs to produce 1 megawatt, and another KPI like the CO2 avoided cost, how much it costs to reduce the tons of emission of CO2, and to compare this KPI with other existing technologies. So, Patrice already said we took two application cases, the refinery case where we produce electricity and also steam for the refinery, and a power case where we produce steam and we send it to a steam turbine to produce 200 of megawatt electricity. I will concentrate in my presentation after more on the power case, 200 electric megawatt, because it's more easy to understand. Then we choose to compare the CNC to other reference technology. And we can discuss it many times, but we choose two different technologies. A technology which is the CLP, which is well known by DPC, because basically it's also technology that's using solid feedstock. So it's easy to compare two technologies with solid feedstock only. And then we also choose to add NGCC burning natural gas. And so you can say why choosing this technology burning natural gas. We are here dealing with the solid landing unit. But when you are electricity producer, the first thing you think to produce electricity is NGCC, because it's the most competitive technology to produce electricity nowadays. So we had taking some hypotheses on the solid feedstock price, which is petcoke for solid, and natural price, so that we can complete these two technologies and give some ideas of the people or why they could choose this technology. And so that's one point. And sometimes also you have this petcoke, you are a refiner, you have petcoke, and then you can complete the CFB and the CLC when you have the feedstock on your hands. So we designed many cases for the two different applications and the different reference technology. Plus, so we did some cases for producing the energy without capture for the calculation of the CAC, or the CO2 avoided cost, and some with capture to do the KPI for the LCOA. So just to let you know the scope of this TEA, so we took the reaction section, we took the flue gas treatment for the both side, air reactor side and the CO2 side for the outlet of the fuel reactor, and the steam turbine. So now we have the design of this equipment, and you need to get how much it costs. So this was done on the Europe case, so it's the euro that has been quoted there for all this equipment. And basically for the reaction section, we went to see some boiler makers or some reactor manufacturers that could give us a quote for these big vessels, 12-meter diameter that Patrice just showed before. We wanted to know how much it costs to produce that, and how much it costs to transport to the place where the CLC unit will be built. Then we went to see some refractory expert company to give us a quote on how much it costs to cover all these internals with refractory, 1, 2, 3 layers. We get also some quotes for the preparation of the feedstock. We went to see also some engineering people to discuss about the flue gas treatment. because I just want to speak with just one more slide after, and also one quote for the steam turbine with Siemens. So just one quote on one slide on the flue gas treatment. When you are on so we had to cope with the air reactor flue gas treatment, which is mainly nitrogen, but depending on the country where you will build the unit, you need to have some emission that cope with the stack emission of your country. So you have to treat probably for particles for the nitrogen. And for the fuel reactor, you are in oxy-combustion there, so you have lower flow rate of CO2, but then it will be higher in contaminants. When you choose to burn petcoke with sulfur, you will have a high concentration on the SOx, for example. So for the CO2 stream, we need to treat it with DNOx, DDUS, DSOx. And nowadays, we see that the CO2 specification is becoming more and more stringent. In fact, we have specification for the EOR specification when you put it back into oil field to boost your production of oil. But if you wanted to store it permanently, there is some project ongoing now, for example, in Norway, Northern Lights, and they are asking very stringent specification for the CO2, because now we need to handle with the ship transport, the pipeline, and so this is to say that you really have to look at your flue gas treatment straight away when you're dealing with the CFC, because it can account for maybe 20% of your capex. And this is really also depending on which feedstock you're using. Professor Lee was speaking of biomass. For sure, biomass, there is no sulfur, so you have a lower capex for your flue gas treatment. So now let's go into the details of this first KPI, which is the levelized cost of electricity. So that's the 200 megawatt electric case. And it was done, a study for CNC build in Europe. So unfortunately, if you want the cost of a CLC in China, it just has to be redone with the China cost. So here it's only a Europe case. And we take some hypotheses. It's a grassroots plant, 25 years lifetime, 3 years construction, a discount rate. We put some contingencies because it's a first of a kind. And we achieve to see that you see in blue the reference case. It's a CFB without capture. And in gray, that's the CFB, and then behind you add the capture unit by MEA, amine capture. And the CLC case is in yellow. And you see that the CLC case, it's higher than the case without capture, but it's in between, it's lower than the case with capture, or the CFB with capture. So it looks like it's economic, it's more economic to build a CLC rather than building a new CFB with an amine capture behind. And then we put some figure for the NGCC case just to compare. But this is really depending on your hypothesis of your fuel price. And here we done some sensitivities for the natural gas price. If the natural gas price is flying up, for sure, that maybe you can see some cases where the CLC can be competitive versus NGCC plus capture. The other KPI I would like to present is the CO2 avoided cost. How much cost to tackle this extra CO2? And this KPI is really depending on which reference case you are taking into account. So if you compare yourself to the CFB without capture, which is emitting a lot of CO2, you will have very low figures for your CO2 avoided cost. But if you compare yourself with NGCC case, reference case, without capture, natural gas burning is emitting twice as less CO2 than solid feedstock burning, then you find again some figures that are more in line with the technology we know, like amine capture around this 80, 90 euro per ton of CO2. This is a figure that we find in the literature for the amine capture. And then again, sensitivity of the natural gas price. So this natural gas price and petcoke price, we want to see where the CLC is optimized versus the NGCC. So we draw a graph where in green you see that the CLC is better than NGCC, and in red it's the NGCC which is better than the CLC. Then this was without transport price. If you add some transport price, and you can see that in the breakdown of this LCOE, the cost of transport and storage can account of nearly 30% of the LCOE. You will reduce the window where the CLC is better, because the CLC burning solid feedstock is emitting more CO2, which needs to be transported. And then with SINTEF, we study a full case. So we add the transport case and the storage to study. So we continue the journey of this TEA to have really the full picture if we want to store permanently CO2. So we study we had some different pressure size vessel and ship size from 7,500 meter cubes or 20,000 meter cubes. And here we found that the low pressure vessels were better, and it was better to use bigger size vessels. But if the carbon intensity was better for the CLC, once you add the shipping, then they're getting very close to each other because they transport more CO2 with CLC. And it's the same for the LCOE, it's getting a bit higher with the transport cost for the CLC. So as a summary, if we stick to solid feedstock, forget about the NGCC, we can say that CLC is more competitive than CFB with carbon capture. With the price we have taken for the petcoke and the natural gas, the CLC LCOE is slightly more expensive than the NGCC with carbon capture. And the delta is increasing if you add transport and storage. But if you reduce your transport cost by building, for example, the CLC very near the place where you store it, and if the gas price is becoming very higher, then you can have some case where the CLC is competitive versus NGCC plus CCS. Very briefly, so just to say that we have done a life cycle assessment for these cases, and as you can see that NGCC is lower in terms of GHG emission because burning gas is emitting less CO2. But when you concentrate on the solid feedstock, you can see that CLC was better in terms of climate change emission. And we've done that also on human health and ecosystem quality, and we find basically the same results. So, as a conclusion, we can say that we can use CLC in refining or power industry to produce carbon-free energy and reduce the CO2 emission. And as already said, it could be also a good idea to use this biomass feedstock to be on a negative emission or to produce biogenic CO2 that can be used for different usage, and even using waste, but that's also another story. So thank you very much for your attention.
Okay, thanks very much for Patrick and Vincent. Any question? I have some questions for Vincent on your PA analysis. I think for NGCC is a combined cycle. Both gas turbine and steam turbine are used in your analysis. But for CFC, I think only steam turbine, no gas turbine. If we want to compare the CFC with NGCC, if we pay attention to normal pressure CFC, of course the efficiency will be very lower than NGCC. For NGCC, the efficiency of electricity production will be 60%, more than 60% with gas turbine, because gas turbine has a very high efficiency, especially combined with the steam turbine. If we want to compare the grouping with the NGCC, I think it's better to compare high pressure CFC. If we operate grouping combustion at a very high pressure, for example, high pressure flow bed or oscillation or recursion, so the outlet for gas stream from both reactor will be very high temperature, high pressure. The high pressure, high temperature stream, for example, nitrogen will go into the stirrer and then combine with the steam turbine. I think in this case, I think it will be compete with NGCC. Otherwise, of course, it will be difficult for CFC to compete with NGCC.
Thank you very much for this explanation. You've done it very well.
But I think for the comparison between CFC and natural gas, I think some other field, some other application will be possible. For example, if we burn natural gas to produce steam for heating, for example, in the winter, we burn natural gas for heating. We burn natural gas to produce steam for oil recovery in the oil company. In this case, I think calculating can also be used. I think it will be better than normal natural gas combustion. I think so. But if we just compare the normal CFC with NGCC, yeah, difficult.
Very nice work and very critical to see the feasibility of CFC and for its commercialized use in the future. I have a suggestion because for the study in Europe market and in China market, the prices are very different. Both for the capex, for the equipment, for the installation, for the capex, also for the OPEX, for the price of petcoke or coal, also the price of natural gas is very different. So we like to have some collaboration together, maybe after this project, to study the economic in China with CFC.
Well, it's true. That's why we need to do some sensitivities on this price. But it's true that this capex is coming from a list of equipment. Each equipment has got a cost for production, for installation, for man hours. So it's some hypotheses that come from a database from an engineering in Europe. And this has to be completely transferred in the Chinese world because it will not be the same price for manufacturing, for installing. So it's going to be redone if we want to do it on the China market, in fact.
Okay, thank you very much for Patrick and Lisa. Yeah, thanks. So,